Good afternoon. Welcome to the last section of the 2020 JRS Sustainability Webinar Series. My name is Charlotte Lee, and I'm from the SATU President's Forum International Secretariat. SATU launched the Joint Research Scheme, or the JRS, in 2012. It serves as a matching platform for like-minded scholars from different SATU member universities to connect and form research collaborations together. Very often, the collaboration started as a team of SATU member universities and then further extended to a broader network with a bigger team. So it symbolizes joint efforts in achieving research excellence across cultures, the experience of which should be shared to a broader audience. That is why we introduced the JRS Webinar Series, where JRS project investigators are invited to share the experience and the latest progress of the project. Today, as a last section, we're very happy to have a chair, Professor Xu Zheng from National Cheng Kung University, and two speakers, Dr. Wen Mariam Wen Ahmad Kamil from University in Malaysia, and also Mr. Wu Sheng Zhan from National Cheng Kung University to share with us their project entitled Development of Energy Efficient and Eco-Friendly Semiconductor Materials for Solid-State Lighting. So without further ado, let me pass the floor to Professor Xu.
Okay. Yeah, and this is a collaborative project from Malaysia and Taiwan. So the title of this webinar is Development of Energy Efficient and Eco-Friendly Semiconductor Material for Solid-State Lighting. So today we have two speakers. One is from Malaysia, from School of Physics, University Science Malaysia, and Dr. Wan Marian Wan Ahmad Kamil, and the other one is my PhD student, Shenzhang Wu, from Department of Photonics, National Cheng Kung University. And yeah, so let me give you a short brief introduce about this project. Actually, this is a 2 years SATU joint research scheme. So I think it's very successful. So let me show you a highlight. Okay, yeah. Actually, this collaboration is not only for 2 years only. Yeah, so I think we can come back to 2014. Yeah, I got a mail from Maya, and she emailed me, said that can we have a potential collaboration? Yeah, I was very excited because she read my paper, right? Yeah, and yeah, and after more discussions, and Maya said that she want to come to National Cheng Kung University to do some experiment, optical measurement. Okay, I say, yeah, that's okay. Why not? Okay, so yeah, after 1 year, she visits NCKU. Yeah, and I think maybe this is a 5 days experiment. And after late, we write the first paper and publish in 2017. Yeah, and okay, and she still send a lot of sample to here, and my student measure the optical lacing properties for her, and yeah, and the other milestone is this one. Yeah, we reactive MOU between USM and NCKU. Yeah, because I think the MOU signed maybe 12 or 15 years ago, and after that, the the time goes to here, and yeah, we reactive. Then we still perform some collaboration, and we publish a second paper in 2020, and we submit two SATU project 2020 and 2021. And yeah, so in these 2 years, we still publish 2 or 3 papers. So I think this is very good collaboration. And yeah, most importantly, in 2021, the summer, we have an online lab tour. Yeah, because my student want to come to Taiwan. However, due to the COVID-19, so this cooperation cannot perform some people's exchange. So and I say, we can have a virtual lab tour. So we perform a environment that maybe 20 or 30 people participate this lab tour, and I introduce our setup and have some demonstration. I think we learn a lot of from here. So yeah, so this is the timeline of the collaboration. Then okay, so today we have two talks. The first talk is given by Mr. Shenjiang Wu, and yeah, his title of his talk is Dispersion Relation and the Condensation of Atom Polariton in Zinc Oxide Microrod, Whispering Gary Microcavities. And the second one is given by Marianne. Her title is Development of Energy Efficient and Eco-Friendly Semiconductor Materials for Solid-State Lighting. Okay, so maybe we can start the first talk. So so the time goes to Shenzhen.
Okay. Oh, yes. Okay, can you see my screen and my laser point?
Yes.
Yes. Okay. My name is Wu Shenzhen, and I'm from Department of Photonics in National Cheng Kung University in Taiwan. And I'm a PhD student in Professor Shi's lab. And the topic today is dispersion relation and condensation of exciton polariton's in zinc oxide whispering gallery microcavities. And in these topics, I will introduce a methodology based on the observation in the spectrum and the geometry of the microcavities. Then we can use this information to calculate the index dispersion of the material. And this is my outline today. Firstly, I will introduce what is the semiconductor microcavities and what are the quasi-particles that we call the exciton polaritons, and what is the whispering gallery modes in these microcavities. And then I will show some experimental results. Mostly are the recombination results in the spectrum of these quasi-particles. And then I will show some recent works that involve the improvement of angle result PL spectroscopy and the observations of the condensation of the exciton polaritons at room temperatures. Okay, semiconductor microcavities. When researchers fabricated semiconductors, usually they can observe some microstructures. In the left figure here, the material used here is MAPBI3. This is a kind of perovskite. And the microstructure shown here is the triangular plate. And this microstructure constructs a kind of microcavity that can confine optical photons very efficiently. And when the external pumping is above the lasing threshold, we can observe multimode lasing behaviors in the spectrum. In the right-hand side, the microstructure is thin oxide microsphere. We still observe many optical modes feature in the spectrum. However, these are not the lasing action. These are the spontaneous emission. The sharp optical modes are because of the enhancement of the recombination rate by Purcell effect due to the high degree of symmetry of this microsphere. So the PPT will delay. The microstructure used here is the thin oxide micro rods. We synthesize these rods by CVD method on silicon substrate. The inset figure shows the cross-section of a single thin oxide micro rod. The shape is hexagonal. This corresponds to the Wu-type structure of thin oxide. And we observe many optical modes feature in the spectrum. This is because the optical photons can propagate inside the microcavities by total internal reflection. And because the optical loss of the total internal reflection is very low, so the optical modes becomes very sharp. And this is the micro PL setup. We use helium-cadmium lasers to do the excitation. This is a kind of CW laser. We use the laser to excite a single thin oxide micro rod on the stage and collect the emissions from the objective and conduct it to the spectrometer behind. The polarizer used here is to distinguish the emission of different polarization. We define TE polarization in this direction, which is perpendicular to a long length axis of the rod. And TM polarization is defined in a direction that is parallel to a long axis of the rod. And this is the multimode spectrum. In addition, the images on the CCD device, the CCD is here. The white images here actually give us another important information. That is the energy dispersion of the material. In particular, we choose a taper-like structure, the thin oxide, to do the experiment. So because of the taper structure, the different position will correspond to different size of the cross-section. So if we scan along this long axis, the observed modes will shift for both polarizations. By using the information of this mode shift, we can calculate the index dispersion as the blue circle shown here. You can see clearly the index dispersion increase gradually when energy approaches about 3.3 eV. This is because the energy is very close to the semiconductor exciton resonance energy. And in order to obtain index dispersion in a wider energy region, we also consult the ellipsometry data from other groups, which are the green circles here. Combine these two parts and apply the Lorentz oscillator model, we can fit the index dispersion as the red lines here in a wider energy region. The Lorentz oscillator model can be used to extract the optical parameters such as the damping term, the resonance energy, or the G parameters. These parameters is proportional to the oscillator strength of the material. So when semiconductor excitons strongly coupled with the cavity photons. This resonance part will make the response of the dielectric constant become bigger if the energy of the photons approach to the resonance energy of excitons. We call these quasi-particles as the exciton politons. So if the coupling strength equals to 0, we can just assume these parameters equals to 0. Then the observed response will reduce to the background dielectric constant only. So these are the EK diagram, the energy dispersion diagram. We take TE as the example. The blue dashed line is the exciton energy state of material. The orange line just reflects the background dielectric constant. And the quasi-particle that the exciton politons will follow the new energy dispersion as the red line here. So the observed optical modes are the solid spheres here. And by the definition of the Rabi spin energy, we can directly extract the magnitude, which is about 200 millielectron volts of zinc oxide. When we obtain the index dispersion, we can use this to predict the curvature of the energy dispersion on the CCD device. The prediction is the red dashed lines. And the white signals is the observations. You can see that the prediction fits the observation very well. However, the prediction actually can tell us the energy dispersion at higher angles. But due to the limitation of the numerical aperture of this objective, we can only collect emissions within about 30 degrees. So in order to confirm the energy dispersion at higher angle, we have to change the method of measurement. So we directly measure the spectrum at different angles by fibers. We observe the mode shows blue shift tendency. And if we plot the trajectories of these modes, we can obtain figures like this one. So you can see the anti-crossing features occurs around the 30 to 45 degrees. Anti-crossing points is around here. These degrees are very similar with the prediction of the red dashed line here. So this also implies the methodology proposed here to calculate the index dispersion is accurate. So in the last part, I will introduce the spatial character of exciton politons. In the left figure here, the semiconductor quantum well is embedded in two DBR mirrors. So the excitons can strongly couple with cavity photons and couple and propagate in this quasi-2D structure. Because exciton politons is a kind of boson particle, so the boson particles can accumulate at the same quantum state within their carrier lifetime. However, because the exciton binding energy of this semiconductor is about 25 millielectron volts, so the phenomena of condensation can only be observed at very low temperature. The exciton binding energy of zinc oxide is about 60 millielectron volts, which is higher than the thermal fluctuation at room temperature. So we did observe the condensation occurs inside the zinc oxide micro rod when we increase the pumping and we observe coherent photons generate at the same energy state. So in conclusion, we provide a convenient methodology just based on the optical modes in the spectrum and the geometry of the microcavity. We can use this information to calculate the index dispersion, and we can extract the optical parameters. And most importantly, this methodology can be generalized to other semiconductor systems with the rate bandgap and large oscillator strength. Okay, thank you for your listening. Thank you.
Okay, thank you, Shen-Chan. So now is open for question or go to the next talk? Then
I think we can go to the next talk first, and then we have the
Okay.
Q&A together.
Okay. So, Mariam, please.
Okay, I take over, Shu.
Okay.
Okay, Assalamualaikum and good afternoon, everyone. Thank you very much for joining us. I would just like to share a little bit on where we are for those of you who have never been to Penang. Actually, we were supposed to come to Penang, right? So, but the pandemic, so we couldn't arrange anything. So basically, just from the bridge, we are just over here, very close to the Penang Bridge. This is the main entrance. And at the School of Physics, my office is at the bottom here, just by this tree here. Okay. So more than welcome to come. So as Prof. Su has mentioned, our initial collaboration started before the Satu application. So we've had several letter of intent, several exchange of emails, and all led to the MOU signing around February 2020, which is during the pandemic. So the signing was using DHL. So, but we managed to have this. Now, this MOU is open for all. If there are any of you from USM, it is open for the entire USM university between us and the National Cheng Kung University, not just between the two schools, but for the whole university. So if you wish to have a collaboration and you need MOU for any grant application, you are more than welcome to use this MOU as well. It ends February 2023, so quite soon. Okay, so we've obtained several grants together, and unfortunately, due to the pandemic, this is a photo by Luke Messi. He won the Nature Photographer Award in 2019. So the title of this picture is actually Lonely. So this is something that we experienced. Our hands were tied during the pandemic. We obtained all the funding, and then when we wanted to go and do all these measurements and stuff in Taiwan, we couldn't go anywhere because of the pandemic. But fortunately, Sue has been nice enough to organize a virtual lab tour. So we did that at the lab, the microphotoluminescent setup, as well as the CVD. And we had the Satu NCK USM virtual handshake. We couldn't do it face to face. We did it online instead. So of course, many email exchanges. So this has been our collaboration during the pandemic. So even though we had the COVID-19, we still collaborated very well. And basically, the semiconductor material that I was choosing for solid state lighting is actually zinc oxide, and we chose that to actually observe random lasing occurring in our sample. So the motivation behind this is for the device to become a potential device for speckle-free imaging. Now, if you base on previous works, not so long ago, it's 2021, it's only last year, they published on how they could actually achieve very good images with very low speckle using random lasing. But they are using dyes as gain medium. So their gain medium is actually a laser dye, which comes with several issues as well. The most inconvenient of having dyes is bleaching, or it will degrade very fast. So we need a solid state gain medium. So this is why we propose zinc oxide as a sustainable gain medium for random lasing and eco-friendly. So it's very much within the sustainability agenda. So for random lasers, since they work very different with traditional lasers, it doesn't have a mirror cavity. So basically we rely solely on small structures. So we rely on the structures to actually provide us the change in refractive index to actually get lasing to occur. So we manipulate the light with these changes in refractive index. The important thing is it works just like a traditional laser, meaning that you still need a pump source, you still need a gain medium, and you still need something to confine the light. Here we are using scattering to confine the light, right? But we also need a pump source, and it can be an optical or an electrical pumping source, right? But to have it by electrical means is tough. You have to have contacts directly on the sample, and to actually create enough photons within the sample is a big issue. So very few reports on this. So we are focused mainly on the optical pumping part. Okay, and the equation, the rate equation related to lasing is very similar, is the same with the standard lasing rate equation. However, we have something called photon diffusion coefficient that we have to look at, because our photons are actually diffused inside and scattered, right? So there is a critical size that relates with the transport mean free path and the gain length. So the transport mean free path is the average distance when the scattered light becomes randomized. Okay, so it relies on these two parameters mostly. So what we did when we collaborated with National Cheng Kung University, we started just by looking at zinc oxide nanorods on glass substrate. It was prepared by a simple method of chemical bath deposition, and we observed that we have a low threshold when the size is roughly less than 50 nanometer in diameter, and the height is roughly half a micron. Okay, the problem is it's still quite high. 0.5 megawatt per centimeter squared is high, right? So the question that we have is, can we reduce this further? Can we actually bring the threshold down for it to become useful devices? And so this is when we start doping our zinc oxide. And when we dope, we notice that yes, we see a reduction in threshold at a certain doping concentration, which is 10 millimolar in this case, still using the same method of chemical bath deposition. The only problem is, as you can see here, right, the size of the structure changes drastically as we increase the doping, because you are working with a concentration that is varied, right? So you have the issue of changes of morphology, right? So we wanted to find a way of, okay, in order to make this, in order to say that the changes, the threshold that we see is due to doping and not just the structure, right? Not due to changes of the structure per se, and also the changes in terms of, you see you have voids here in between them. So filling factor also plays a role. So we decided to actually, okay, let's look at a better way of making this. This is by changing the temperature. So we fix the amount of concentration, and then we vary the temperature, and we observe that we see different, with the different temperatures, we actually see different amount of aluminium, okay, different amount of doping. And from that, we see that, yes, okay, at a certain temperature, the lasing is very good. Certain temperatures, the lasing is not so good. Okay, so the lowest threshold was in this sample, 110 degrees Celsius, and this actually had the highest doping. So the highest doping gave the lowest threshold. Okay, and what we notice is that there is a red shift in our lasing, right? So at what we did is we did single shot lasing spectrum, as you see here in A. So we saw this red shift at around about 1 milliwatt pump power, this photo. And this is very similar to the photoluminescent spectrum that we actually observed. So there is something called the band tail effect that is occurring in our sample due to doping. Okay, And this gives rise to changes in the energy, or when you get the photoluminescence, you will see this peak, the luminescence peak coming here instead of here. Okay, so this is due to excess oxygen or excess zinc. In our case, it's excess oxygen. So we see this in our sample, which give rises to this change, right? So basically, it shows the possibility of tuning the wavelength of a random laser with the presence of doping. So this is what we are trying to prove. Okay. Then we started to introduce a capping layer. So this is an idea by my student Abdullah. He has already completed his PhD. So we want to add another layer on top that has a different refractive index. So the problem is we wanted to make sure that it did not cover the whole rod. So it will only cover top part. So it looks like cotton buds when we see the FISM image. So we made sure that it only covered the top part, and we noticed that when this is around 100 nanometer, or basically lambda over 4 of the wavelength of our laser, we noticed that we had superior lasing. Okay, so lasing was very good. Threshold was also very good. So this is something that we observe, and to look at this further, to understand the effect from SiO2 further, we actually did, we call this, I forgot the actual name, finite element method, yeah? So we use finite element method to actually identify, and we notice that well, 100 nanometer of SiO2 layer, it shows wave guiding properties with the mode spectrum long enough to tolerate several periods longitudinally. So you increase the intensity of the light strongly. So we see more confinement of light occurring when we have actually around 100 nanometer of the SiO2 layer. So these are the things that we have done. Most recently, we've just received the email of this publication on Sunday. So this is the most recent work that we did together, and it's by looking at gold dope random lasers, which shows quite good lasing characteristics as well, when again with the highest doping of gold that is possible in the chemical bath deposition method. So the main thing is we want to maintain this. You see the height here of the nanorods is all maintained at roughly the same height. Changes of that would show changes in other changes that can affect random lasing. So we wanted to make sure that this was fixed. So we tried to make this as fixed as possible. And so we were sure that the lasing was caused by, the difference in lasing threshold was actually caused by the doping itself. So our future outlook, as we are moving towards making device usage, we thought about flexible nanolasers. So we thought about implementing optical fibers with zinc oxide. So the idea we have is to actually put zinc oxide at the tip. Okay, but so far we've done on the outer layer, and we have some preliminary results with Taiwan. So hopefully we can publish soon about this, because I have to say there is no preliminary result on fiber-based zinc oxide random laser out there. So we may be among the first to actually publish this. So this is good. So we are in the middle of completing our setup. Thank you very much to Prof. Su, who would always answer our emails on any query about this. So thank you very much. And in order to actually achieve this, we are already collaborating with FlexiLicate. This is a local company that creates optical fibers. So we are tuning some parameters of the optical fibers, and we hope that we can get some random lasing output out of this for a more practical device in the future. So that's all from me. Thank you very much.
Okay, thank you, Mayan. Very nice talk. So I think the time is open for question. So any question? or comment from audience. If you have some question, you can raise your hand or you can leave your question on the right hand side. Any question or comment?
Our audience are usually quite shy. It may take some time for them to to think about the questions, to organize the questions.
Okay. Yeah. So maybe I have a question. Mayan, and can you introduce some simple preparation of the gold dope zinc oxide rod, how to do?
Yeah, it is still using chemical bath deposition. So it's using the same method as we had aluminium, we just replaced with gold. That's why it's a very simple process. We grow basically the chemical bath deposition is done together. Is while we are growing the zinc oxide, it is together with the doping element. So I think maybe in future, if we really want to maintain the size, maybe we have to do external doping instead. Maybe your CVD technique is better, the chemical vapor deposition method for doping. But we've not tried, so it's open for more avenues.
Okay, thank you. And I think one question from the audience, Harslen, say, can Dr. Mayan elaborate more on the wave guiding behavior? Can you say more?
Oh, okay.
Your
Must have tough question. Okay, let me share back the. Okay, not entirely sure elaboration on the wave guiding, but basically we use the finite element method, which is console multiphysics software. So basically we just investigated the lateral confinement. Let me just share back. Why it's not coming out now? Share button. Okay. Okay.
Yes.
Okay, I believe it's this line. Okay.
Yes.
So basically, we just investigated the lateral confinement. So it's just XY axis, 2D structure, and this part here is the zinc oxide nanorods. Okay.
Yes.
So we try to form it. We try to make it as simple as possible, just to get the thoughts over. Basically, when we have the Si2 layer, which we put it as a circular part here, so this we define the refractive index, and it's different with the refractive index of ZNO, and of course it's different with air. Outside is just air, so the refractive index is just one outside. And so we made sure that this axis is the Z direction, or basically the C axis orientation when you consider the material itself grown that way. And what happens is when we have this light confinement, you have the wave guiding to actually be happening inside the zinc oxide nanorods compared to when you have just bare. Okay, so the bare one has leaky modes, as you see here. It's not as so when you have it in a very light color of red, yellow, it's a very strong confinement, strong modes. So the propagation from this, when you have the propagation inside the rods, this will give out with much stronger light confinement, basically. In simple terms, this is what it means. So when we actually what we actually notice is that the thickness plays a role. The thickness of the Si2 layer, it's roughly quarter of the wavelength in order for this effect to occur. If it's less than that or more than that, you still get lossy modes. There is that part as well that we notice. Hope this answers the question.
Okay, thank you. So I think Shenzhen, your system is the size is larger than the Mayan's one, right? So
Yeah, micro.
yeah, so my micro rod. So I think your Brisbane game mode is a lateral direction. So your longitudinal direction is some waveguide effect. Can you comment on that for your case?
Yes, the size of the micro is much larger, and the surrounding scale or the confinement for micro rod were better than narrow rods, but that's the difficult part to investigate the narrow rod systems. Yeah, so I might ask a question. Just Professor Mayam, you mentioned that the doping will make the gain spectrum shift, right? And what is the energy regions of the optimal gain in your system? Because it will affect the multiple lazy, right?
The what gain?
The gain spectrum
Oh,
of
we
the
don't know the gain
doping.
spectrum.
Yeah, after doping, yeah.
Yeah. The thing is we never measured the actual gain spectrum, so we are not sure on the amount of gain that it achieve.
Yes.
Which should change also the threshold as well as where the wavelength of that leasing would happen. Yeah, it's something that we could not measure in a way within our limitation, of course. But I predict that the shift it's because of when you have changes in the energy of the system, overall it kind of perturbs the entire system to actually come out at other wavelengths. So I think the gain curve has shifted. I think it has. But how much it does shift is something that we did not actually measure.
Okay, but
Sorry,
it will show blue shift tendency for gold doping, right? Okay, I think it's good because the emission of zinc dioxide in UV region. So if you can extend the gain spectrum toward long wavelengths, it's an advantage for this material, I think.
Yeah. Maybe Prof. Su can add further on this. He knows best.
Okay. Yeah, I think there are a lot of work we need to do. Yeah. Okay. And any question or comment from audience? You can raise your hand or leave your question on the right hand side. Okay, maybe I have a question to Shenzhen. Yeah, you mentioned that you can achieve the atom Photon Leasing, but how about the application?
Okay.
For energy efficient lighting or something like that?
Okay. Can you see my screen?
Yes.
Okay. I think it's a very special character for this quasi-particle because in the past, the condensation of both Einstein occurs in the atomic system, but that has to be at very extremely low temperature, about 0 Kelvin. But because the quasi-particles here is combined with the semiconductor exotons and the cavity photons, so the mass is much lighter and the critical temperature can be increased, so we can observe the phenomena at much higher temperature. And because the difficult part of this application is that the carrier lifetime is very short, which is about the picosecond scale. So it's very hard to observe the condensation behaviors actually if you do not do any modulations such as the potential modulations by the plasmonic. So it is now is a field in the investigation. I have not seen any application so far, but in principle, the threshold will be much smaller than the traditional lasing threshold. The order may be 1 or 2 order of magnitude lower than a conventional laser in the same systems. So I think the most amazing part is that the threshold can be dramatically reduced if we can achieve the condensation of the exoton polaritongs, because this is a novel coherent light source applications.
Okay, thank you. So when you achieve the exoton polariton lasing, you can reduce the lasing threshold up to 1 or 2 order of magnitude lower than the conventional one. Okay,
Yes.
great. Okay, and yeah, for Luo Fangxi, I have a question. Can Dr. Mayan explain why did you choose to dope zinc oxide with aluminum and gold?
Okay, so sorry, what's the name?
Fangqi.
It's the law.
Chi.
Oh,
Okay. Sorry, I'm very bad at pronouncing the names. But basically, we chose aluminium. The first choice was aluminium because of the way of our process. So chemical bath deposition, not every doping works well in chemical bath deposition. So the best recipe out there is for aluminium. So this was why we chose that, because we are not so much concerned on the recipe. We are more on concern on how it behaves under optical pumping. What kind of laser characteristics do you get out of it? So we are more interested on that part. So we chose whatever recipe is best from literature, and that's how we move on. Now gold and silver, technically by using all these metallic, okay, this relates to the next question, why we use aluminum and gold to reduce the lasing threshold. It's because we wanted, well, initially our purpose was to create these are metal elements, so you should be getting some plasmonic happening. But because the size is too small, so when you just dope standard doping, so the size is too small for it to have a plasmonic behavior, which I think Prof. Su can correct me on this. If we have the plasmonic behavior, we can reduce the threshold even more, right? But with the behavior of doping, you actually change several things, even though you are not getting the plasmonic effect, because you change the structure of your material. So initially you have a good structure. When you start introducing dopings, you introduce extra atoms within your semiconductor material, right? And these extra atoms can actually give rise to defect states. Too much defect is bad, but just nice is good. So we have to find what is the just nice amount for it to be good. So this is, and it reduces the threshold because you start increasing the scattering. Now you're talking about very tiny amounts of scattering. Now the moment you can enhance the scattering in a sample to a point that the scattering is to confine the photons. So basically the scattering has to be something that keeps the photon inside the sample long enough for lasing to occur.
Mhm.
If the scattering is just to get the light go in and just go out straight away, then we don't get anything either. So so we have to create that atmosphere for them. So it's like an optical cavity for them through the scattering. That's how I understand it. Prof Su can correct me if I'm wrong there.
Yeah, yeah. I think the doping is an art. I think like he can change a lot of things. Yeah, not only the doping concentration but the morphology change. So I think we have a lot of work we need to do to understand why the latent threshold can be reduced a lot, maybe 1 or 2 or magnitude. Okay. So any question? I think the our audience are quite satisfied about
Because it's
this
in-depth and very
discussion.
comprehensive.
Yeah.
May I ask the last question?
Okay, please.
Please.
Professor Mariam, what is the
I'm
best
getting
season
many
to
questions.
travel to Malaysia?
Yes, Wu, sorry.
What is the best seasons or months to travel to the Malaysia?
Oh, anytime. We are the same. We don't have 4 seasons. We have the same season all around.
Okay.
We have a bit of rainy season, so maybe end of the year is not so good. Yeah, I think
I've not
similar
been
to
to
Taiwan.
there.
We're on the same line. So where are you coming? Together with Prof. Su.
Okay.
Okay. Yeah.
Do let
Yeah.
us
We
know.
would like to go.
Yes, please come.
Okay. Okay. I think there is no question from audience. So let's thank two speaker again.
Thank you very much for joining the section. I know some of you actually joined all the 6 sections. That is really supportive of you. So thank you very much for joining, and thank you again for Chair Professor Shu and our speaker, Mr. Wu and Dr. Mayam. So I hope for the rest of the audience, I hope you enjoyed this section. So this is the last session of the series. We'll see you next year. Thank you very much. Goodbye.
Bye bye.
Bye. Bye. Bye.